Grade 11, we are on our second day of Money Matters. Yesterday we did some mathematical exercises with percents and decimals, so we'll make sure that's still good to go. And then we talked about simple interest and compound interest. And today we're going to look a little closer at those two wonderful ideas. So the first review thing that we're going to do is just recall how I would write, sorry, I'm playing with my calculator here, how I would write 25% as a decimal. So we've got to just be really careful with this. I know you know how to do it, but if you had 25%, it means 25 over 100. So whenever you get your percent, you can just do a quick division if you would like, and you would get decimal 25. So some of us recognize that it's always two places behind the decimal for percent, which means hundredths. So if I had 312%, I would take my 312 and divide it by 100 and get 3.12. So I have moved two of those behind the decimal. 6.1% dividing by 100, I could write it as divide by 100, or remembering that divide by 100 is moving the decimal to the left twice, my decimal would be decimal 0.61. 2.19%, moving the decimal twice to the left, would be decimal 0.219. And lastly, decimal 258%, very, very tiny, especially if we're talking about money, would be, move the decimal to the left twice, decimal 0.0258. So we'll just take care when we're doing those. All right. If you want $1 right now, going to take you $1 out of your pocket. If, however, you thought about that last week and you saved towards getting that $1, you would have invested less than $1. So say you had 80 cents and you invested it with your Uncle Louie and it earned some interest. It would be less than $1 and you would earn interest until you got your $1. If you wanted $1 now and you had to pay it off later because you just couldn't wait to have that $1, it would cost you more than $1 because interest would be added to it. So here's the big idea. If there's something that you want to buy, it's going to cost you way, way less if you start to save for it ahead of time and earn interest on your money, as opposed to take a loan right now and pay it off later. So there's the preaching for you. Okay, Carolyn's grandma gave her $1,000. She invested it for 4 years at 4% per year, compounded annually. So that means our banker is putting interest into her account every year. And it's going to be 4% compounded annually, and that's an annual interest rate by Canadian law. Okay, so at the beginning of our story, she invests $1,000, and in the first year, that earns 4%. So she earns $40 interest, so that at the end of that year, she has $1,040. So how did I get that interest? I did $1,000 times my interest rate, which is decimal 0.04, and I got $40. So I added that on, and now she's got this much. The next year, she earns a little bit more interest, and this time her interest is on $1,040, so she should earn a tiny little bit more, and she earns her 4%. $1,040 times 4% is $41.60. So she earns a little bit more interest. We'll add that on to the $1,040. She now has $1,081.60. Another year and another 4%. But she's earning that 4% on a slightly bigger number. So the interest should keep going up a little bit every year because she's got more to earn interest on. Times decimal zero 4, $43.26 this year. So I take my 43.26 and I add it to the $1,081.60, and we get $1,124.86. One more time. Interest is added for that last year. We take the amount that's in the bank and we give it another 4%, and she earns, you're really trusting me with this calculator, aren't you? $44.99, which is added to that total. 24.86. Here we go. $1,169.85. So Grandma invested $1,000, and what she ended up with in the end was $1,169.85. So the interest that Grandma earned on that money for doing absolutely nothing other than leaving it alone is $169.85. Not bad. But I tell you what the banker doesn't like is having to do the calculations year after year after year after year. Surely there's a formula that we can use. Yes, there is. From last unit, we know how to find the amount if we have an initial value and a rate of growth, and it grows the same year after year. Our equation should look like exponential growth that we looked at last unit. So we need to think about, just a second, I can't spell and talk, exponential growth. There we go. We just need to think about what is that rate of growth. Initial value is 1,000. I'm growing, so it's got to be bigger than 1. I'm growing at 4%, so 1.04 is my rate of growth. Let's just check that if you invest $1,000 for 4 years, we will get that same amount. 1,000 times 1.04 to the power of 4. What do you know? $1,169.86. I made a rounding error somewhere. I apologize for that. So there's an equation that we're going to need to keep up handy somewhere, although we've already seen it. Our amount of money is the initial value. We're going to call it P because now we're kind of talking about banking stuff. So they're allowed to pick the words. Is the principal, that initial amount that you started with, times, okay, we want our money to grow. So 1 plus the interest rate as a decimal to the n, which is the number of times they figure out your interest. In this particular example, they put interest in every year. That's not always the case. So we'll just write down number of compounding periods. Okay. So how many times did they put interest into the account? Goes for the exponent. Okay. Mark borrows $3,000 to buy a tractor. But you can't buy a tractor for $3,000 at an interest rate of 4.75% per annum. So you have to get a yearly interest rate. There we go in Canada, compounded annually. So that means every year they're going to put interest on that loan. He plans to pay back the loan in 5 years. So he's just going to hang on to that $3,000 and hopefully he'll have the money 5 years from now to pay it back in one lump sum. How much interest will he pay? Well, let's figure out how much he owes first of all. So the amount of Mark's loan should be the amount that he borrowed, and it is going to grow because he's going to owe that $3,000 and some interest. So we want 1 plus the interest rate. And we're going to figure out how many times they add interest to his loan. So whether you're getting the interest or you're paying the interest, the formula would be the same. So how much does he owe? He started with a $3,000 loan. The interest rate was 4.75%, so I have to move the decimal 2 places to the left to divide by 100, or percent, decimal 0.475. And N is how many times they do the interest, put it into his account. It's for 5 years. The exponent would be 5. And just like that, 3,000 times 1.0475 to the power of, oh, I didn't check my typing. There we go. To the 5. $3,783.48. So it costs him, the interest costs him $783.48 to take that loan. Now, we don't always put interest into accounts or onto loans once a year. Often, it's more often than that. It could be compounded twice a year, could be compounded every month, often every month. So by Canadian law, they give us an annual interest rate. So say that you got a loan for 12%, and they're going to add interest to your loan twice a year. They can't put 12% on your loan twice a year, or you're going to go totally broke. They're going to take that 12% and divide it in half. Because it's semi-annual, they're going to be doing it every 6 months or twice a year. So we're going to cut that interest rate in half. It kind of makes sense. You do 6% twice a year instead of 12% once a year. If it was monthly, we would divide by 12 and get our monthly rate. So we're going to divide by 2, semi-annual. If you have 18%, how much would that be twice a year? Cut it in half, 9%. A monthly rate. We're going to take 18% and divide it by 12. We would get 1.5% per month. Okay. I'm going to ask you and your friend to fill those last few out together. Let's go down to example number 3. Copy and complete the following table. The top row provides an example. So, if you are adding interest to your account for 5 years, and they are compounding your interest or putting it in annually, that means 5 times they're going to put interest into your account, just like normal. But what if they put interest into your account twice a year? That means they will put interest into your account 10 times. So our N value, our exponent, would be doubled twice as often. If it's monthly, they're going to add interest to your account 60 times over the course of those 5 years. If you were going to leave your loan, your investment in the bank for 10 years, and they compounded it yearly or annually, they would give you interest 10 times. If it was semi-annually, they would give you interest 20 times. And if it was monthly, 120 times you would be given interest. Can you and your friend complete that chart together as well when you get to class? Okay, here's another example. Sophie puts $2,500 into a registered retirement savings plan that earns 7.5% per annum. That's a good rate. And you can get good rates if you're going to leave something in an investment for a long time. Determine the amount of the investment after 8 years if the interest is compounded annually. So here is our equation. The amount that Sophie has depends on her initial value and her rate of growth, which is 1 plus the interest rate to the power of n. So for A, the amount that Sophie has is $2,500. The interest rate, if it is compounded annually, is 7.5% just as normal. So I'm going to have 1.075 for my rate of growth. The number of times it's put into the investment over 8 years is once a year. For 8 years, that would be 8 times. So my exponent is 8. This would be my I. Okay, let's type it into a calculator. $2,500, power of 8. $4,458.69. Pretty good. That's a pretty good interest rate. B. So nothing changes. Her investment doesn't change, and the interest rate doesn't change. But what happens if we change it to semi-annually? So the I value is going to change. They can't give you 7.5% twice a year. They'd go broke. So they're going to take their 7.5%. I'm just going to write it as a decimal here, and we're going to cut it in half. So they're going to give us half each time, but do it twice a year. So let's get started here. Our formula will be $2,500, but this time the rate is half, decimal 0.75 divided by 2, decimal 0.375. Okay, 3.75%, but twice a year. So that means instead of 8 times adding interest, they're going to do it 8 times 2 times 16. So you'd think it would end up in the same place. Same amount of money, same amount of time, same interest rate, just compounded differently. So I'm just typing this in, and we end up with $4,505.57. So you actually end up with more interest the more times it's compounded. Last is C. If the interest is compounded monthly, so let's see if this is true. Maybe I lied to you. $2,500. Our rate is going to change, and our number of compounds is going to change because we're doing it more often. So our interest rate would be 7.5%. I just wrote it as a decimal, but divided by 12. Okay, 1 decimal. Decimal 0.75 divided by 12. I bet you it's going to be ugly. Oh, not too bad. Decimal 0.0625. I did no rounding. I wrote the whole thing. My N value is how often they give her interest, and that's going to be for 8 years. Every month, they are going to give her interest. It sounds like it's a gift, doesn't it? 8 times 12 is 96 times they're going to put some interest in, but a very, very tiny rate, because that's only a monthly rate. $2,500. Times 1.00625. So that's decimal 625%, very tiny. But to the power of 96 gives us $4,546.80. So you can see you get more money if you have more often, if it's compounded more often. Not like hugely more, but certainly some more. And if she invests it for 25 years, what a great deal of difference that would make.